So today we're going to look at existence and uniqueness theorems for initial value problems. We had some techniques for finding solutions that we already saw to initial value problems, which again, what's an initial value problem? It's a differential equation with specified initial condition. But we never said, under what conditions can we guarantee that at least one solution exists. We also didn't say under what conditions can we guarantee that no more than one solution exists. So that's what I want to talk about a little bit today. That we in fact have two theorems that I want to go through. And they're kind of wordy, so I have them just typeset and we'll kind of look at them rather than writing them out. So there's two theorems, one for first order IVPs and one for higher order linear IVPs. So for first order IVPs, these are the two theorems that we're looking at today. I want to start with this first order one. So what do we have here? We have a differential equation, right? Y prime equals f of xy. So as soon as you see that y prime equals f of xy, what do you want to picture? So let's move this out of our way. We won't need that for a little while. You want to picture a slope field, a direction field, right? So picture the differential equation as, imagine this as a slope field, right? So we have, you have some x and y and some function f of xy that is specifying a slope at each point, right? So slope, 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 right? You have a slope at each point. And, I didn't specify a formula here for f of xy, so I'm just kind of drawing some random little tick marks to indicate slope, but this is the image that you put in your head. Then you have an initial condition, a comma b, right? Or y of a equals b. So picture this as a point, a comma b. Is how you want to imagine that. So you now have some point in the slope field, and so let's say maybe it's there. Maybe that's the point a comma b, right? And then what is a solution curve from that point? Well, a solution curve from that point is some curve that flows from that point and follows all the arrows, right? It has follows the little tick marks that are specified in this slope field, right? So that's the image that you want when you see that given information. Now, with that IVP, we have first a uniqueness condition. So we say that there's at least one solution, an existence condition, as long as this function f of x, y is continuous on some rectangle containing the initial condition, right? So that's how you want to view this R. R is some rectangle. So let's do R in blue here, right? So this is some rectangle that contains that initial condition. And so I'm saying that it goes out to some point a plus epsilon, a minus, delta is be consistent with my notation here. So a plus delta, a minus delta, it goes to the right and to the left by some delta. It also goes up and down from that point to some values, b plus epsilon and b minus epsilon, right? So that's the rectangle that we're talking about here, right? So this region is a rectangle R, and we're saying that as long as the slope field, the values of the slope field, f of x, y, as long as they're defined, it's a continuous function, then there will definitely at least exist a solution to that initial value problem on that rectangle, right? So maybe, so it definitely exists at least on that rectangle. Maybe then over here, it has an asymptote or something and stops existing, right? Maybe it blows up later, but at least on that rectangle, there will exist a solution. But if you're only given those conditions on that first bullet, there might be multiple solutions, right? So that's where the second bullet point comes in. How do you know there aren't multiple solutions? Maybe there's this, but then maybe you have another solution curve up here, right? Is there some second solution curve? So that's the second part of this theorem, right? If furthermore, the partial derivative of f with respect to y, right? So that's this symbol here, right? Partial derivative. Notice there are little curly d's instead of straight d's. So partial derivative of f with respect to y, meaning just treat x as a constant and take a derivative treating only y as the variable. If that is also continuous on the rectangle, then there's a unique solution. Right, so those are the two conditions here. So first, I want to look at kind of a non-example of this, case where we don't have some of these conditions satisfied and we have multiple solutions, right? And then we'll look at some places where these conditions are satisfied, and thus we can conclude that there's only one solution. So let's start with a non-example here, right? So let's look at, I'll get rid of the second theorem for now, because we'll look at that later. So I want to look at, for example, let's consider the differential equation y times dy dx equals minus x with initial condition y of 2, sorry, let's do y of minus 2. Y of minus 2 equals 0, right? So this is our IVP. Right, so this right here is our initial value problem. I have a first order differential equation and initial condition attached to it, right? So this is our initial value problem. So I claim that both the function y1 of x equals 4 minus x squared and y2 of x equal negative 4 minus x squared. I claim that both of those are valid solutions to that initial value problem. Right, I claim these are both valid solutions. And how can we see this? Well, you can check it just by plugging them in, right? So check by plugging them in to both the DE and then also the initial condition, right? So if you try this to show, let's do this, right? First, let's look at equation. First, let's check y1, right? So y1, does it satisfy the differential equation? Well, let's see. What's the left-hand side of the differential equation? With y1 plugged in, it's root 4 minus x squared times the derivative of 4 minus x squared, which is 1 over 2 root 4 minus x squared times chain rule, all right, negative 2x. So that's our left-hand side. And then we simplify. So the 2's cancel, the roots cancel, and we're left with just negative x. Oh, well, that's the right-hand side of the differential equation, right? So that's exactly the right-hand side is negative x. So that checks out. And then for the initial condition, let's see, does that work with y1? Well, if I take y1 of minus 2, I get square root of 4 minus 2 squared is root 4 minus 4 is 0. So, yep, it satisfies the initial condition also, right? But now we can check y2 also, right? So what happens here, it's very similar, right? It's the same, exactly the same function, but with a negative sign, right? So we plug in for y, then we do the derivative. All right, well, that's just an extra negative sign sitting out in front of what's otherwise the same derivative. Because we can kind of factor that negative out of the derivative anyway. So now the two negatives cancel, the 2's cancel, the roots cancel, right? And again, we just get negative x, which is the right-hand side of our differential equation. And then the initial condition is not affected by that negative sign because it's 0 anyway, right? It's negative 4 minus, or negative square root of 4 minus negative 2 squared, right? So that's negative 0, which is still 0, right? So there we go. We absolutely have two different solutions to this initial value problem, right? So because we have two different solutions, then this initial value problem must not satisfy the conditions of this theorem. This theorem must not apply to this initial value problem because we're witnessing one that has two different solutions, right? And if we check, so here's our conclusion, right? Our conclusion is that the given IVP must not satisfy the conditions of the uniqueness theorem. And in particular, what must not be the case? It must be that the partial derivative must not be continuous on R. So then if that partial derivative isn't continuous on some region, some rectangle containing the initial condition, then we can't guarantee that there's at most one solution, right? And here, since it's kind of arguing in reverse, right? Since we saw two distinct solutions, we know that this condition must fail. So they call that kind of argument contrapositive, right? You're saying P implies Q. Well, I observed not Q, therefore I can conclude not P is an argument by contrapositive. That's exactly what we're doing here. So let's analyze this. So let's find let's get our function little f. So what is little f? Look at the statement of the theorem. It says y prime equals little f of xy. So little f is whatever is on the right-hand side of that differential equation, right? So I have to solve it for y prime. So here, the way I wrote the differential equation, it's not solved for y prime, right? It's y times dy dx. So I have to divide both sides by y. So let's get our dE solved for y prime. And sometimes this is called normal form. Actually, I don't use that terminology a lot because the poor word normal is overloaded with so many meanings. But regardless, this is how we have to write our differential equation. So divide both sides by y to get y prime equals negative x over y. Right. So this tells us now, see the right-hand side of this, that's your function f. Right, so f of xy for this particular initial value problem is negative x over y. Right, so now you can do the partial derivative of this with respect to y. So if I do the partial derivative of f with respect to y, just treat this as you can treat x as a constant, treat this as an exponent, and then you can just do power rule, right? So we get xy to the minus 2. So it's x over y squared. So this is discontinuous wherever y equals 0, right? So if you're thinking about our plane, our little slope field, if you have x and y, right, where's y equals 0? Well, that's all these points here, right? So these essentially are bad points. These are places where the partial derivative of the right-hand side of our differential equation is discontinuous. So along the x-axis, we cannot promise a unique solution that's what this is saying, right? Because the partial derivative is discontinuous there. We actually could anywhere else in the plane. If you took an initial condition strictly in the top half or strictly in the bottom half of the plane, then you could, but along the axis you can't. If you pick an initial condition there, then you can't. And sure enough, our initial condition, right, was this point minus 2 comma 0. Well, that was right in the bad zone, right? It was right where that partial derivative was discontinuous. So that's why we had two different solutions, right? We had, in this case, we had y1, right? We had y1 of x was root 4 minus x squared. And then we had a whole second solution, right? Which was down here. We had y2 of x, right? y2 of x was negative root 4 minus x squared, was a whole second solution, right? So we did not have a unique solution coming from that initial condition. And the reason is it's absolutely impossible to bound that in a rectangle in which the partial derivative of the right-hand side of our differential equation is continuous. It just can't happen because the whole x-axis is full of discontinuities, right? And that initial condition is sitting right on that x-axis. So that's why we had non-unique solution here. You could have a case by random chance where there's still just a unique solution, even though it failed the conditions of the uniqueness theorem. It's not if and only if. But it doesn't. But you can't promise that there's only one solution. And sure enough, here's an example where there were two. You might notice too. These look a whole lot like circle equations, right? They should. And what is happening? Well, if you look, this differential equation, this is really just saying that the slope is negative reciprocal, right? Think of y over x versus negative x over y, right? Those are the circles had to be the solutions to this differential equation, because this is saying if you have, this is just a little bit of, and this isn't necessary for the uniqueness theorem, but just a little aside on some geometry, right? At some point x comma y, what is being specified as the slope? The negative reciprocal of y over x, right? So y over x would be the slope of that line, and then we're saying negative x over y. So the perpendicular to that line, that's what's being specified as the slope here, right? And that's true for any point in the plane. Over here, what's being specified is the perpendicular to that line, right? And then, what's being specified here? There's, at this point, we're being specified, the slope that's being specified is the perpendicular, right? So you could draw the slope field here by just drawing the negative reciprocal, the perpendicular, at every point x, y. Well, okay, now imagine what kind of curves are gonna have all of those as tangents. Well, circles, right? Because the radius is always perpendicular to the tangent on a circle, right? So that's why you can have circles, right, hitting all of those perfectly tangent. But a circle itself isn't a function. So that's why we're having two different, that's why from this initial condition, that's why we have two different solution curves. The top half of the circle, which is one function, and the bottom half of the circle, which is a different function, right? So that's, which is how I constructed the example in the first place, right? So I used geometry. I'm sort of, popping the hood or showing you my methods, I guess, right? That's how I built the differential equation, right? Is just start with a little bit of geometry and then use just write that down as in terms of slope, so then you can find the solutions based on geometry. Now, of course, this differential equation is also separable, and you could solve it using separation of variables. But here you could do it just with geometry. So, all right, so that's our that is our non-example, right? That's our example of an IVP that did not satisfy the condition there in the uniqueness theorem, and sure enough, there were multiple solutions, right? Okay. Now, I should also mention that we're just sort of talking about this theorem and trying to understand this theorem. I'm not proving this theorem, right? I'm just sort of seeing the theorem in some examples, but I'm not proving it. The proof is that there isn't a great like 100, 200 level mathematics proof of this theorem, at least that I've ever seen. The key idea goes back to, where this comes from, really comes back goes back to the work of Cauchy in 1839. And it just uses a little bit more analysis than typically you have seen at a 200 level. It uses some ideas, kind of like uniform continuity, and you'll see those things down the road. Lipschitz conditions, uniform continuity. So, all right. So that was our first example. I want to show another example, and here maybe is this one maybe is a little bit more satisfying because we're going to see the theorem apply instead of see the theorem not apply. So let's use the uniqueness theorem to prove this property of logarithms. Say we wanted to prove this fact, that log of a times b equals log of a plus log of b. Right? This is true for positive real numbers a and b. Right? And this is kind of a profound result when you think about it. If you're thinking of logarithms as defined as the area under the curve 1 over x, why the area, from 1 to 2, why that area plus the area from 1 to 3, if you add those areas, why that should be exactly the area from 1 to 6, right? Right. If you define natural log that way, that's a really profound statement, right? It's not obvious at all that those first two areas should add to that other area, but that's exactly what this is saying, right? That natural log of 2 plus natural log of 3 equals natural log of 2 times 3, which is 6. Right. So let's see if we can prove this theorem using the uniqueness theorem. So let's look at the variables. So a, I want to call x, our independent variable, right? This is the variable that we're going to differentiate with respect with. And you can leave it as a, but then all your derivatives are going to look like dda, and I just want to write ddx, so I'm calling that x. And then we're going to let b, right, be arbitrary, but a arbitrary fixed constant. Right. So then I'm going to define the two functions that I want to prove are equal. Right. So let's define f of x equal to log of x times b, right, which we'll call bx, and g of x to be log of x plus log of b. Right. So we wish to show that f equals g. This is our goal, right? If we can do that, then we've proven the identity that we're trying to show. So at the moment, I haven't really done any math. I've just given names to everything, right? So I want to show that f equals g. And here's how I'm going to do it. I'm going to do it by showing that f and g both are solutions to the same IVP, and that same IVP has a unique solution, right? So the idea then is that if they're both solutions to that initial value problem, but that initial value problem only has one solution, then they must just be two different names for the same function. They must not actually be different from one another. They must be equal, right? So it's a very nice way to structure an argument. Let's dive in here. So the first thing I have to do is I have to come up with the IVP, right? So let's define the IVP to be as follows. So what pieces of information do we need? Well, we need our differential equation and we need our initial condition. What should these be? Well, we want these to be something that F and G both satisfy, right? So I'm going to start with the initial condition because it's maybe a little bit easier to see what that should be. The initial condition I want is y of 1 equals log of b, right? Where did that come from? Well, often we pick our initial conditions at 0. Here I don't want to do that. Log is undefined at 0, so you don't want 0 as your initial condition. Let's pick 1. That's probably the next easiest value, especially for log, because log of 1 is 0, right? And you could look at both of those functions and say, okay, if I plug in 1, I'm going to get log of b. And we'll check that more carefully, but that's where that would come from. Now I also need to say what the differential equation is. So I need to specify y prime. So y prime here, again, it takes maybe a little bit of looking at. What would y prime be for both of these functions? Well, it looks like it would just be 1 over x, right? For g, that's not too hard to see. It's a little trickier for f, but also not too bad. So let's then carry this out, right? So and again, if you're wondering where this comes from, just basically just taking the derivative of f, taking the derivative of g, and looking for some relationship, right? That's what a differential equation is finding some relationship among the derivative of your function and the function itself. So this is our IVP. Now, what I want to do next is I want to verify carefully that f is a solution, right? So let's check the differential equation. Well, the differential equation, left-hand side, is y prime, right? So I'm going to take f prime. And what's the derivative of f? It's 1 over bx times b by the chain rule, which is just 1 over x. Great, that's the right-hand side. Right? Then I'm going to do the initial condition for f, right? So I'm going to do f of 1. And what is f of 1? It's log of b times 1, which is log of b. Well, and that's good. That's our initial condition. That's what that should be. So I showed f is a solution. Now I'm going to show that g is a solution. So the differential equation, left-hand side, is going to be now the derivative of g. Right? So the derivative of g, that's just 1 over x plus 0. Right? The derivative of log of x is 1 over x. The derivative of log of b is 0 because it's a constant with respect to x. So that's 1 over x. Well, that's, again, the right-hand side of our differential equation, so that's good. Then I want to do the initial condition. Well, g of 1 is going to be natural log of 1 plus natural log of b, which is 0 plus natural log of b, which is natural log of b, right? So that's good. So f and g are both solutions to the IVP. So that means one of two things is the case. Either the uniqueness theorem doesn't apply to our IVP, and this is an example kind of like the circle example up above, and they're just two different functions that both solve the same IVP. Or if the uniqueness theorem does apply to the IVP, then it means f equals g. It means they're not two different solutions. They're actually the same solution, just written in two slightly different ways, right? So, and it's going to be case 2, right? The second is what's going to hold here. So let's now show that the uniqueness theorem applies to our IVP. So in this case, what is the initial condition? The initial condition is the point 1 comma log of b, right? That's the initial condition. And we also need the partial derivative of the right-hand side with respect to y. The right-hand side of our differential equation is 1 over x. So the partial derivative is actually 0, right? Well, that's continuous everywhere, right? So it's continuous in particular in any rectangle I choose around our point 1 comma log of b. Right, so I can say the uniqueness theorem applies, and the IVP has a unique solution. Right. All right, great. Well, what does that mean? F is a solution of that IVP, G is a solution of that IVP, but it has a unique solution, therefore F equals G. It must have just been two different symbols that actually corresponded to the same function, because otherwise we would have contradicted the uniqueness theorem and found two different solutions, right? So thus, F of x equals G of x, right? So we showed, well, let's explain that in writing, right? Because, once again, because both solve the IVP, but the IVP has only one solution. So they really must be the same, right? Two different names for the same solution. So that's arguing by uniqueness. So that's the end of our proof, right? And that proves that property of logarithms, right? That log of a plus log of b equals log of a times b. That proves that those functions have to be the same by our uniqueness there. So kind of a cool way to argue, right? An old identity that you certainly saw back in maybe college algebra or pre-calc, right? But it's a cool differential equations proof of that identity. All right. So that's an example and a non-example, and then an example of first order differential equations, and the existence and uniqueness theorem here. Right? I also want to show this second order theorem, right? So I mentioned there's a whole second theorem, and I want to talk about this one now, right? So this higher order theorem. This one, so we have this as, we have an extra condition here, higher order linear IVPs. So this is a lot more restrictive. It's not just y prime equals any formula you can imagine, but so it's more restrictive in that way, but it's less restrictive in another way, in the sense that there could be second derivatives, third derivative, fourth derivatives, as many derivatives as you can imagine. Any finite number of derivatives, right? As long as the equation can be written in this form. So this form, this is the form of a linear. This form specified here, this is the form of a linear DE, right? And basically what we're saying is we need those coefficients. So your coefficients are all functions of x, p1 of x, p2 of x, up to pn of x. And then g of x, the right-hand side, is also a function of x. Those all need to be continuous on some interval containing the initial condition. And as long as you have that, then there is a unique solution, right? So this one, you actually don't need any partial derivatives. You just need to check those coefficient functions, make sure they're continuous, make sure your equation is linear, and then you can say that there is a unique solution. Also notice here, we need the right number of initial conditions, right? This is saying that it's an nth order equation, and there are exactly in initial conditions, right? So that's also saying that you need the right number of initial conditions. The first order equation just takes one initial condition. Second order takes two initial conditions, and so on. So let's do an example here, right? So let's find all functions that satisfy the following property. So let's say I want the function to equal the negative of its own second derivative, and I want f of 0 to be 1, and I want f prime of 0 to be 0. Okay, so this is my what I'm tasked with here. I want to find all functions that satisfy the following properties. All right, well, these properties, they're not too messy. I might be able to get at least a solution, maybe not all solutions, but maybe a solution I can get just by guess and check, right? So let's just take, let's just sort of do some educated guessing, based on, I don't know, sort of famous functions, right? What kind of functions become negative of themselves if you take their derivative twice? Well, sines and cosines kind of do that, right? Like if you do the second derivative of cosine, you get the first derivative of cosine would be negative sine, and then the second derivative of that would be negative cosine. So cosine does that. But then sine works that way too, right? The first derivative of sine would be cosine, second derivative would be negative sine. So sine and cosine both satisfy that condition of being equal to the negative of their own second derivative. Now, how about these initial conditions? I want the original function to be 1 at 0. I want the first derivative to be 0 at 0. Oh, well, that's just cosine, right? Right. So yeah, f of x equals cosine of x works, right? So we were able to kind of just intuit a solution here, right? Cosine of 0 is 1, and then cosine prime would be negative sine, but then negative sine of 0 is 0, right? So that satisfies all of those. Okay. So I found one solution by just kind of poking around because the situation was fairly simple. Oh, and I'm tasked with finding all functions. Wait, but maybe there is only one solution to this set of properties. That's exactly what the theorem tells us, right? So if we can apply the uniqueness theorem, then I can say that there aren't any other solutions, right? Let's apply the uniqueness theorem to show that this is, in fact, the only solution. That we already have all the solutions. This one solution is the only solution. Right, so how can I do that? Well, I need to show that this differential equation is linear. So I have to write it in that form. So let's write it as f double prime plus 0 f prime plus 1 f equals 0. Right? Why did I do that? Well, I wanted to write this differential equation in this form, the form of a linear differential equation. That's what I wanted to do because I can't apply the theorem unless the equation is linear, right? And it is, right? So this shows that our differential equation is a second order linear DE. Right, and what are the coefficient functions? I have P1 of x is the constant function 0, right? P2 of x is the constant function 1, and g of x, the right-hand side, is the constant function 0, right? Constant functions are continuous everywhere. In particular, they're continuous on an interval containing our initial condition. And it's a second order equation, and we have two initial conditions, right? Second order equation because it's a second derivative. There's two given initial conditions. So the uniqueness theorem applies. So this lets us conclude cosine is actually the only solution to that IVP. Right? So there's an example where we can apply the this higher order theorem, right? The second order existence and uniqueness theorem. All right, so that's our two theorems, right? First order existence and uniqueness, second order existence and uniqueness. And, you know, we had, in particular, we had one case where the preconditions of the theorem did not apply, right? We did not have a continuous partial derivative. And sure enough, there were multiple solutions, right? There doesn't always have to be multiple solutions just because the precondition failed. But in this case, there were, right? There was a top half of the circle, bottom half of the circle, two different solutions. Then we had a case where we found an IVP where the precondition did apply, right, to this IVP, and we found two different solutions. Therefore, those solutions must have been equal, right? And that proved a little log property for us. Kind of a cute example, right? Then here we had IVP where we were able to kind of guess one solution and then apply the theorem to show that there couldn't be any more, right? So that we actually fully solved the higher order initial value problem with the theorem and a little bit of guess and check. So, all right. Thanks. There's the existence and uniqueness theorem.